Okay, good morning. Let's get started. The class looks lean today. Even the whole building looks lean. Right? I don't know why. If I walk in through the corridor, it seems like most of them are gone. I hope people are not enjoying the spring. Right? Didn't look like spring anyway. So we're still kind of behind. I think we are running about 3 lectures behind on this module. But still, we need to cover 2 important topics. So we'll finish that before going on to the file module on Monday, right? So, and there's no new handout because it's continuous from the handout from yesterday, right? So we kind of left off here. We're trying to figure out how much frames to give to each process, and there's a notion of a minimum number of frames, right? And I kind of ended at that point. Is that clear why you need a minimum number of frames, right? It's linked to how the whole procedure works, right? If you don't have a particular frame, you get a page fault. Remember the 6-step process you go through, right? You have a page fault, you find the free frame, you bring a new page, then you restart the instruction, right? And if your one instruction cannot finish because it'll keep seg faulting, then you could page faulting, then you can never make progress, right? So for example, in this particular architecture, it's possible to have instruction in such a fashion. In the worst case, it might need 6 frames. So if in this particular scenario, if you only give it 4 frames, it can never make progress because it brings the first 4 frames, you get a page fault, it has to replace one of its own stuff. So that particular instruction can never finish. It'll go into this infinite loop of do a page fault, bring a page in, and restart it, then find that another part of the instruction cannot finish, and so on and so forth, right? So on this particular machine, you need at least 6 frames. It's not something you worry about in the modern machines because memory is free, right? There is no reason why you should be running memory constraint unless you are running on a PDA or something like that, right? Most modern machines, I think like a gigabyte of memory costs like $40, $50, something like that, right? So there is no reason why we should worry about it to that extent, right? The other reason why you may worry about it is if you have so many processes that you give up all the memory to all the processes and you're running low, right? And in that situation, it should not happen either. You should not be running thousands of processes on a single machine kind of thing, right? So these problems should not happen, but you should be aware of why this might happen, right? Because you at least need to have your instruction proceed. We'll see a more insidious thing with the same kind of similar kind of problem in a subsequent in a few more slides. That's called thrashing, and that tends to happen a lot, right? In fact, if you were noticing, you might have noticed it happening for the IE browser, right? I started IE and it said not responding, wait for a little bit because it's trying to get more pages, and we'll see what that is, right? So in terms of allocation, the problem is you have a whole system. How do you do a procedure which is good for the global stuff or for the local process? And this is a challenge which happens throughout the system, right? You have a number of processes. Each process belongs to the same system. How do you give resources based on which process, right? So you could either give the same amount of memory to all the processes. You can give it based on how much memory it wanted, right? So the first model is equal. So regardless of how much you asked, I give an equal number of memory to each of them. And clearly that's not going to be a good idea because then some which don't need a lot of memory are going to get more memory. Some which need a lot of memory are not going to get a lot of memory, right? And if you believe that processes which need a lot of memory are more important than processes which don't need memory, right? For example, your PowerPoint is going to need a lot of memory because it's a big program, it's a big process, so it's going to need a lot of memory. And your like something which displays a clock on this machine may not need a lot of memory, and it tends not to be that important, right? So you would like to give more memory to the bigger programs. So you may think of the next model where you give more to a program which needs a lot of memory, right? So what's the bad thing which can happen with this model if you just give more memory to a program which asks for more memory? The first one, we talked about, it may be some small programs never asked for it. But here there are programs which are asking for a lot of memory. There are some which are not asking for a lot of memory. Would that solve all the problem, or do we have to think about something else? Can you think of a process which is small but needs a lot of memory, or which is large which should not be given a lot of memory? You don't have to assume that all processes are good, right? Want to take a stab? For either case, can you think of a large program which should not be given a lot of memory? How do you write a program which needs a lot of memory? Can you think of a simple way to write a program which needs lots of memory? A complicated way is to have a complicated big program which needs lots of memory. What's a simple way to write a program which needs lots of memory? Yes?
Just like allocate a really big array and don't do anything with it or something?
Yeah. Memory is what you ask for, right? So you could really do a good job. I mean, hopefully PowerPoint is not trying to ask for a lot of memory, but it just has to because it's a big program. You can write a bad program which, if you need a 512 by 512 array, right, you can ask for 1024 by 1024, right? How many of you, when you write programs, when you write arrays, how many of you do exactly what you wanted, and how many of you just allocate it a little bit more, right? It's okay to say, allocate more, right? Most of us allocate more because there is no cost to you, right? When you run the program, the system does not say, I'm going to charge you for the memory, right? So typically, I see people, when they write the program, they don't calculate exactly how much memory they want. They ask for more because they figure something magically should happen and give you what you wanted, right? So if you just do this, then it's very easy to get a lot of memory. So if you have a program and you know this is what is happening, all you have to do is create large arrays, never use it, right? Since your program was big, you get all the frames. And we'll see, because of the working set model, you'll actually get better performance, right? Which means that your program maybe will get 50% of all the frames, but your program only actually goes through a little bit of memory. So you can use all the 50% to be running really good. So you can use this to make your program run better than the other program by basically. So you as a programmer, when you go beyond the college, when you're trying to write a program for a living, you try to figure out how Windows Vista does stuff. So you can figure out how you can defeat it to get the best performance, right? So if you find out that Windows is actually doing this, then basically you ask for a lot of memory, never use it, and your program will run faster, and other things in the system will run slower, but you don't care because your customer is going to be happy, right? So we don't really want things to be that simple because there's always something. So as operating system, you're trying to figure out how to do it in a fair fashion such that malicious users, in this case, you try to use some of the stuff, right? So how can you fix this? How can you fix the notion of, so it's good to give different memory to different people, right? We kind of agree with that, right? So we want to give different stuff to different people. So if you're not going by how much memory you want, what other way you can think of to give different people different memory? If you're Microsoft, what would you do? If you're Microsoft, I'm assuming that you want your programs to run good, right? I mean, you don't want your programs to run bad. So how do you make sure that your programs will run good? You can do something which sounds kind of illegal, which is kind of look to see if the process is PowerPoint, in which case give it 50% memory, right? You could do that, right? And if you figure that's happening, then you can basically change your program to PowerPoint.exe, right? You start a new company which does inventory control, and the program is called PowerPoint because you figured If it's called PowerPoint, it's going to get out of memory, right? So you could do that, or you can look at at the priority, right? You can see if it's a interactive job, if it's a background process, it's a higher priority task. You can use all these things. So there's no one science. You're basically trying to figure out how to give memory to different processes such that the ones which need the most gets more memory. The ones which don't need the most at least get some, and you're trying to be fair, right? And you always make the decision. And one of the other ways you do that is through priority. The other way is to look at the amount of page faults you're causing. And you go through all this stuff to figure out how you can do this such that it's fair and the processes don't tend to abuse that, right? Because if you abuse this, then you get better performance, and you don't. So as operating system, you want to be as fair as possible, right? So there are a whole number of different policies that each one does. So that's one of the ways that they tweak it as time progresses. Different Windows XP and Vista and all those things. You can have the same operating system, but tweak the way memory is allocated to different processes. And the reason why you tweak that is modern machines have more memory. Modern programs are bigger, right? Your PowerPoint 2007 is bigger than PowerPoint 2003, and so on and so forth. So programs want more memory. You have more memory. So now you're trying to figure out how to do the stuff so you can keep all the people happy. And that's exactly what you try to tweak, right? And that's one of the reasons why you don't want to run a very ancient operating system on a new hardware, right? So you would expect that if you run Windows 2000 or Windows 95 on a modern laptop, right? Most modern laptops can easily have 2 to 4 gigs of memory, right? You don't want to run the Windows 95 on this machine because it's never seen that much memory. It was not known that you can have 4 gig of memory on a laptop when Windows 95 came out in 1995, right? You probably had like 64 megs or something. So that operating system is going to be very stingy in how much memory it's going to give. It's not going to run as good on the modern machine, right? So the next goal is to do the global versus local. How do you make a decision for the global system versus local? And you'll see this in other scenarios. You'll see this in the file system scenario and all those things, where if the operating system figures out that it can do something globally good, right, then you want to do that, which means that it might decide that your program is running, PowerPoint is running, it gave you a certain amount of memory because you're running, and now the PowerPoint is running here. So for the global good, it may be better to take away some pages from you and give it to the PowerPoint, right? Which means that you might have been happily running along with a certain amount of memory. Suddenly you begin to get page faults for no fault of yours. You wrote a program, you tuned your program, you made sure that your program is not going to do too much page faults because you wrote the program nicely. Right? If you're writing an array program, you access it a certain way and everything. Your program starts running, and then your pages were taken away from you halfway through. Right? You never saw it for the homework project because we assume that you're the only one who was running, right? But imagine you got all the frames you wanted, halfway through, half the frames taken away from you, right? And you'll begin to get page faults for no fault of yours, and hopefully the global performance is still good, right? And how to get that right it's much more challenging because the system now is taking away memory from you, and you may be unhappy because you spent all this time optimizing your program. And somehow you have to prove that whatever you did on the global scale, all the programs were, on average, they're running better, even though you are being penalized, right? Rather than just a local allocation. And how you go about that is something that you worry about. So all these things are very important for the OS developer, and it's not very hard to imagine how you can tweak this stuff, right? So if you sit down and think about it, so if you look at the pin trace for a long time, you just sit there and you figure out what your program is doing, and you're trying to figure out how you might tweak the system to make your program run good. And you keep doing that for next program, and so on and so forth, right? And that's one of the reasons why it takes a while for the developers to come to the new version. You don't see Vista coming out in a week or so because they're trying to analyze how systems are evolving. And this brings up the issue what we kind of alluded to, which is the notion of thrashing, right? So what happens is when you don't have enough memory, right? You do a page fault. You have to run the page replacement algorithm. You have to send something to disk. You have to bring something back to disk, right? So if you're doing really well, then your program should not get any page faults, right? If your program is running a certain way, you should get the page fault rate as low as possible, right? But under certain circumstances, your page fault rate will be very high, even though you're doing something good, right? So the notion of thrashing is trying to quantify what page faults are okay and what page faults are not okay. What page faults should be avoided, what page faults could not be avoided, right? So can you think of a page fault which cannot be avoided? You actually did this on a homework project, right? So you should know. Yes?
The first time you access that page, I think.
Yeah, the first time accesses, you will get a page fault, right? So even if I give, in the case of wherever you gave all the memory that your program wanted, you still got the page fault equal to the number of pages, right? The first time you ask for a page, you get a page fault, right? So anything more than that is not something you don't want, right? So where do you get page faults? So this is exactly what will happen in your system. Your system, if you look at the CPU utilization is affected by the page faults, because when you're doing a page fault and you're waiting for something to come from the disk, right, your CPU is not being used, right? So as you kind of increase the number of processors, it keeps going up. At some point, it just crashes. You know, it's all the time. All it's doing is bringing stuff from the hard disk, and you might have noticed it because your laptop. You might have noticed sometimes the disk grows crazy. You can do nothing on your system. It just kind of sits there, and the disk is going wild because it's trying to bring more pages, right? So let's look at the notion of why page faults work, right? Like Adam pointed out, you need to at least pay the cost for page fault once, right? So if you wrote a program which says like, yeah, A equals 1, B equals 1, C equals 1, right? If this is all your program, right, you will have to take the page fault depending on how the memory is laid out. You'll have to take the certain number of page faults, your program finishes, you're done, right? This is a trivial program, not that interesting. But typical programs, you assume go through loops, right? Let's say you go through a while loop here, and you go through it goes through a while loop here, right? So the idea here is typical program does some computation, goes through a loop, does some computation, goes through some loop, right? If you assume this is what the program is happening, what it's doing, essentially if you unroll this loop, it becomes, you come here and you keep going back and forth on this stuff for a long time. Then you go through this and you go through this for a long time, right? So paging system does not really help if the program goes straight line through, because paging it basically brings the pages on demand. But since you're going to go through only once, right, you might as well bring it at the front or at the middle or what have you. You're not making any gain, right? Where you hope to gain is, at this case, if you pay the price to bring the page once here, you hope to use the same page throughout this loop. The longer the loop, the more benefit you get out of the system, right? You paid the cost to bring it here, and you hope to use it throughout this loop, right? And you hope to unlearn whatever you learned here. When you go from here to the next loop, you hope to replace all these pages with all these pages as soon as possible, and then use it throughout this loop. Does that make sense? This is the fundamental reason why we want to do demand paging, right? We want to do demand paging because we assume that the programs don't use all the memory all the time. We know that they are going to use only some of them some of the time, but they're going to be using it over and over again. So if I can bring it here and keep it in memory, all these are going to go through with no page faults. And if I do this rough stuff right here, all these are going to go through with a page fault, and I can do this transition, right? In real systems, where you fail is this transition, because you kind of look at the past to learn how the accesses are being done, and then you have to suddenly unlearn and then learn that this is a new loop, right? So that's one of the reasons why the LRU cannot keep using the history for a while, because at this point you're going to a different loop, and you want to kind of keep this stuff, right? So what happens if the number of frames you have only is equal to, let's say here. Let's say you wanted in this loop 10 frames, but you only have 8 frames. What would happen? You're going through sequentially, right? So let's call the frames that you wanted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or let's say 0 to 9, right? If you're going through in a simple loop, you're going to do 0, 1, 2, and so on and so forth, right? So you're going through a loop means that your page request will be 0, 1, 2, 3, 4 up to 9, 0, 1, 2, and so on and so forth, right? That's clear, right? That's how you're going to ask. This is the instruction thing. Suppose you have only 8 frames. You only have 8 frames. What would happen? Right? Let's say 0, 1, 2, 3, 4, 5, 6, 7, right? Now you have 8 and 9, right? Can you think of a policy that you can do, LRU, MFU, whatever you can think of? Which one would you replace? Which one would you replace which you expect to give you good performance? Can you think of like what would be a good policy which can replace the pages here such that you get good performance? Does any policy sound better than the other one? Some of you nodded no, right? You can't really do much here because whatever you replace, the next one is going to be 0, 1, 2, 3, 4, 5, 7 through 9, right? So you can do LRU and then replace these two, right? And then you can do 8 and 9. But then the next one immediately goes. So even though this was the least recently used, right? So you are here, right? From here, this was least recently used. But if you look in the future, this is going to be used pretty soon, right? But just because even if you can look in the future, you can't really do anything because it's going to be, all of them are going in a loop, right? So what will happen is at this point, you're going to have lots of page fault, right? So every loop through here, you're going to have a page fault because you're going to do this kind of a stuff. You may avoid a few of those, but essentially through every loop, you're going to see at least 2 page faults. And you lose the performance benefit that you really expected to get, right? Each loop you're doing this page fault. So what really happens is your program, we call this the working set, right? Your program working set is 10, which is the number of frames that it's kind of going through all at once over and over again. So that's the amount of memory that it's working from. And if you give it less than what it wants, if you give it 8 frames, if the working set is less than what it wants, then you're going to go through this case. Because your program says, I'm going through 10 frames over and over again, you have to at least give me 10. If you give me less than that, whatever policy you do, you'll have to do a page fault. You'll have to see more page faults, right? And this is the notion of thrashing. If you go to this case, the worse it gets, right? So if you, instead of giving 8, if you give it 2, right? Then every other instruction will cause a page fault. And you're going through this loop, you expect some things to happen, and you're going to go through a lot of page fault. So what that means is, your program will run for a few pages, they'll cause a page fault, it'll replace some page. If it is returned, it has to be returned back to the disk. It'll bring the new page in, and then next instruction will access the next page, which has to be replaced. Something gets returned, something gets brought back. Then you move forward, something gets returned, something gets brought forward. So if you think about it, essentially every page, you modify it, write it to a disk, bring another page in, modify a page, write it to a disk, bring something back. So you're basically operating on the disk. You're basically writing something to the disk, reading from something to the disk. So when this happens, you'll notice that your system just basically, the disk will go crazy. How many of you notice that? How many of you notice a case where you're running a program and suddenly all it does is the disk is going wild? You can't kill the process, it's basically doing this stuff. And if you have an older hard disk, you can hear the hard disk go wild, right? right? You must have seen it, right? And it's especially very easy to create if you write a bad program, write a big program with a lot of memory, right? And you'll begin to see this thrashing. I mean, write a program with lots of memory and then randomly access a whole bunch of memory, right? Your program will begin to thrash, right? When it's thrashing, for people who noticed it, are you able to kill the process? Are you able to get control and kill the process immediately? No, you can't kill the process immediately, right? You want to guess why you couldn't kill it immediately? It takes a while to get control, right? Usually if a process is behaving bad, you can go in and kill the process, right? But for this case, you can't really get in and kill immediately. You'll have to wait for a while. Sometimes you just can't do anything. You have to just reboot the machine because it's just so slow, nothing gets done, right? Do you want to guess why the process cannot be killed? Even though the operating system is getting control all the time. Every time you get a page fault, it goes to the operating system, it brings the next page in and brings the whole next stuff to go, right? But it does not let you give control to you. It does not let you do much with it. Can I guess why? So what happens is remember when you want to kill a process or something, when the operating system gives control to you, right? The process should be in a good state, right? It cannot be half here, half there kind of stuff, right? So when you get a page fault, it tries to bring the next page in. The page fault routine goes much at higher priority than giving control to you, right? If it's halfway through instruction, it has to bring the next instruction back and let it make some progress before it gives control back to you, because it does not want to give control to you halfway through the instruction, right? So when it's doing this page fault, it says, okay, you have to wait because I'm halfway through instruction. I need to bring this next page in and finish it and give it control back to you, right? So it takes you longer and longer to wait for the stuff because this is more of an autopilot kind of thing. It's because this is fundamentally it has to finish the stuff to get the instruction back, and you can't really interrupt it. So you have to wait for a while for some instructions to finish so it can give control back to you. And most of the time you just sit there, right? And that's a bad thing. So you want to avoid this is called thrashing, and this happens because your working set is more than what memory was given to you, right? So even though you don't run into the problem that we talked about before, which is the minimum number of memory needed for a particular instruction, you will run into this, right? You will run into this. So when will you run into this? You'll run into this when the working set is larger than the amount of physical memory given to you, right? How big do you think your working set will be? Do you know, is it like a number, or do you think it's something that has to be, it depends on the program? In this case, it is 10, right? Can you think of a reasonable number, or this is something that has to be computed? It turns out it has to be computed because it depends on the program, right? So the programs evolve, programs change. So you may look at some programs and say 10 seems to be a good number, but programs may come up with different numbers, right? So you want to calculate what the working set is. So if you have a good operating system, so you can either do two things. One is you can assume that this does not happen. If it happens, you just crash and then you reboot the machine, you're good to go, right? That's one way to go about it, which a lot of operating systems seems to do it. But let's assume that you're a good operating system. So if you can calculate what the working set is, then you can give it that much memory. So then you'll be good, right? So you don't have to reboot the machine. So that's a good thing, right? If the working set happens to be larger than what the total physical memory is, then there's something you can do. But otherwise, you can help the system, right? So how would you calculate the working set of a program? Using the techniques we learned so far, right? Meaning MMU has this reference bits and all those things. Operating system only gets control every so often. This is similar to one we looked at in the last lecture. How would you find out what is the working set of a program? So one way you can do that is every so often, right? Again, this is the clock interrupt which happens in the operating system. Every so often, at this point, US operating system go in and make the reference bit for all the program 0, right? So in this case, you are, so if this is all in the memory, make them all zeros, right? And let the program run, right? The next time you get control back, either at this point or so, see which ones were accessed, right? If this was accessed, this was accessed, this was accessed, if everything was accessed, that means within this interval, all these pages were accessed. So within this interval, they were all in that working set, right? You don't know what a working set is, but you know that in the last interval, all these were accessed, and these certain pages were not accessed. So you can make a guess that in the future, those are the ones which are going to be accessed. So you can assume that these are part of the working set. You can assume that these are not part of the working set. And if all of them are accessed, then you can kind of assume that the working set is larger than what you want. Then you can give it more memory, right? So this is one way to kind of learn this by having a reference bit, right? What would be the problem with that approach? Would that really work? Would that really help you figure out what the working set should be? You can look at the illustrations on the board, right? So every so often, we don't know what the time is. Obviously, that's one concern. You have to figure out what the time is, right? What will happen if the time is too long? So instead of doing every second, let's say you do every minute, right? And you're trying to find out all the pages that are accessed in the last minute. Yes?
You'll probably include a lot of stuff that is being accessed anymore from the past. You're not using it anymore.
Yeah, so if you look at this case here, right? You would like ideally you would like the time to be sort of like here, right? If it's too long and you included the whole program, then you're including this working set and this working set, right? So you want it to be smaller. So that's one of the things you want to figure out, right? You want to figure out whether it's this working set or this working set and not the whole one, right? Regardless of what you do, this last loop and this loop would mess up things. Suddenly it's going from one to the other. But hopefully it's such a fashion that you don't see the stuff, right? The other problem is, if you look at these pages, right, if you're only using one bit, right, you're going to see that all these pages will count as 1, and all this will count as 1 too, right? You're going through some set of instructions here, which are going to cause page faults, but they're only being accessed once, right? So it'll be good if you can have a counter which says that this was accessed 10,000 times, this was accessed 1 time, this was accessed 10,000 times. So this is part of the working set. These, we don't really care, they're accessed only once. This is probably sequential code, right? So the hardware gives you more than a bit. If it gives you a counter, then you can use the counter to see how many times it was accessed, to see how many times you are looping. If it accessed only once, we don't really care because that's probably a sequential execution. If it's accessed a lot, it's probably a loop, right? And then hopefully the time is good enough that you capture this working set and this working set and not this one, right? And if it turns out that this is a larger loop and this needs like 20 and this needs 10, right? If everything was working fine, you would be able to figure out that at this point you're accessing 10 pages, I'll give you 10 frames. At this point you need 20 pages, I'll give you 20 frames. You'll get messed up when you go from here to here because for one time you'll think you need 30 pages, 30 frames. See, you need 10 of here, some of here, and some of here. But hopefully if you have this count, and hopefully if you age the counts properly, you'll be able to guess these things such that I give you the number of frames you need to avoid thrashing, right? This will be the ideal thing to do rather than doing this globe and all those things, trying to figure out how much you need to reduce the page faults and let you do that. And again, this needs hardware support. Again, you need the operating system to get more complicated, set these bits, read these bits, and all those things, right? It may not happen for most of your desktops or laptops, but these are one of the things that you can do for when you're running a server, right? So it kind of adapts. So basically, once you start here, you may get a certain number of frames, but once your working set gets cranking, you'll learn that you're going through 10 pages over and over again. I'll give you 10 frames. So that's kind of optimal. You only need 10. Giving you more is not going to help you. Giving you less will hurt you really bad. And so you're going to run optimally. When you switch over to the next one, I'll give you 20. I'll let you run. So this will be a good global and local policy. There's more overhead, but if you don't do that, you'll get thrashing, right? If any of you haven't noticed thrashing, if you have a desktop and it has enough memory, right? And if you're good at hardware, take out some of the memory modules and let it run, right? Don't do this before a project is due, but run with like 64 meg or something on your desktop, right? It'll be so painfully slow, right? That you will kind of give up and understand what's going on, right? And so that's that. So does that make sense? So can this be solved simply by just buying more memory? Rather than doing all this complicated stuff, can we just solve the problem by buying more memory and just do whatever the operating system does? In fact, I think that's the model that most of the desktop operating systems operate on, right? They don't do any of this checking, but they just figure that if your disk is too slow, buy more memory, you'll be fine, right? In fact, that's one of the advice you can give for most home computers. If you go to most of your friends and relatives who are not computer literate, right? Most of the machines you can make them go much faster by just putting more memory. You don't have to understand what the policy is and all those things, but typically it tends to solve most problems, right? Tends to make things go faster. And that's pretty much, if you go to the like Best Buy or something and the guy basically will say the same thing, right? Yeah, just put more memory, you'll be fine, right? It's not a smart thing to do, but it works for the most part. And especially since memory is so cheap, right? So essentially that's what you're trying to say. So you're looking for these localities. If your program has no localities, if it's a straight line program, then the whole notion we studied in this lecture is sort of wasted on you, right? But nobody ever writes a program which is one long straight line of code, right? Unless it's a trivial program, because it's just boring to write one long straight line of assignments and printers. You go through loops because you iterate through data, you do stuff over and over again, and you want to find the working set. So that's the notion of the working set. You use Greek symbols to explain those stuff, but essentially you're trying to figure out how many pages you're using in the past, and you're using that to predict that this is what you're going to use in the future. So if I find the correct number of frames that you're using and call that a working set, if the number of pages the frames that you get is equal to your working set, then you'll have good performance. Essentially all of them are in your memory and you keep going forward. And if it's not, you thrash, and thrash essentially is a notion of you're getting more page fault than you have to. So essentially you have to use some way to look at the past, right? So you have to figure out how far back to look at. And since you can't do this at the instruction level, since you don't have the page frame trace and all those things, in real systems, operating system has to sort of booby trap the pages every so often, right? And see which pages were accessed, and then it figures out what the page frame rate is, right? And again, the problem I mentioned, if you just have a fewer bits, then you don't really understand which is a loop and which is a straight line code. If you have only one bit, you just know that the page was accessed. But if you have a larger counter, then you can get a sense of which frames are being accessed a lot and make some inferences, right? So ideally, if you have like 10 bits and stuff, and if you have a little bit shorter thing, if you keep the number of time units small, then you can learn what this is and make the stuff. This adds overhead to the operating system. So most operating system commercial ones just ignore that. But if you're a server, you want to deal with this stuff because you get better performance, right? Even if you have a lot of memory, you still can allocate different amount of memory to different processes to get good performance. So you do worry about this if you're worried about performance. So essentially what the systems at some point do is they know that the page fault rate is good, right? So one simple way to solve all these problems would be to say, figure out how much page faults you're getting. If you're getting a lot of page faults, then give you a little bit more memory. I don't know what working set you have and everything, but sort of set a bound. If you're getting too much page faults, I give you more pages, right? And hopefully that'll help you. It'll fail if you're a runaway program and you're taking down the system. In fact, you'll take down the system with you because now you're getting more and more pages. But otherwise, most of the times this sort of thing works, right? To get a sense of what we're talking about, so if you look at the Windows, right, task manager, can you see it from the back, right? If you look at the Windows task manager, it tells you each process, how much it has. And so one of the lines I have here is the memory usage, how much memory you're using, what's the peak memory you have used, how many page faults you've seen, and what's the virtual memory sizes, right? The virtual memory size will not be the same as your memory that you're using, right? In some cases, virtual memory is actually smaller because of the sharing. So some of the libraries are shared, so they're counted as memory that you're using, even though they're not part of your virtual memory. And if you look at those, there are some processes which have lots of page fault. If you look at the first one, there's a process here which is 382,000 page faults, right? Do you know what that program is? MC Shield?
Yeah, it's the virus scanner.
Yeah, the virus scanner, right? So why is the virus scanner getting so many page faults? Guess. We don't know how the operating system policy on this machine, right? Why is the virus scanner getting so many page faults compared to PowerPoint? And PowerPoint here is 74,000, but the virus scanner has lots of page faults, right? The virus scanner tends to run for a long time. It's also a lower priority task. I mean, you don't want it to be the highest priority in the system, right? So it's easy to steal memory from that because you don't want it to be. If I want the slide to come up, I want it to come up. I don't want the thing. So it's easy to steal memory from it, right? It's running on the sort of the background, so it keep losing all the pages because it's not running all the time. So when it's not using, somebody steals it from it, so it gets a page fault. So these background processes tend to get more page faults because they were long running, sort of in the background, and so any page they use gets stolen from them more often than something in the front, right? It is probably running for a while too. So there are other issues that we'll notice. One is the notion of so like Adam mentioned, every process has to take a certain number of faults because that's what it needs to bring the memory in, right? So one way to avoid that is if I know all the pages, just pre-page it, right? So when I start the process, rather than starting everything fresh, I kind of bring the first certain number of pages, right? In fact, operating systems get more and more smarter. They kind of figure out what they kind of learn, right? So they can kind of see, you keep using PowerPoint over and over again, and I know PowerPoint, when it starts up, typically gets a certain number of pages. If I can remember what those are, next time I start PowerPoint, I bring all of those immediately for you, right? So after a while, your system gets faster and faster, right? So if I can do some of these stuff, then even though the page fault has to happen, it may not happen while you wait, right? So even though that I need to bring in 400 pages, I can bring the 400 pages immediately. So it might take you, it might look like the first few pages you have to wait. The other ones, while you're doing something else, they're brought before you want it, right? This is called prefetching. We'll use a lot of that in the next module. You bring it before you want it. If you are good at predicting this stuff, then things look like it's going really fast. If you're bad, you pay twice the cost, right? So for example, if I'm going 1, 2, 3, while I'm at 1, if the system can bring in 2 and 3, right? So when I come to 2, I may have to wait. But when I come to 3, it's already there. So it looks like you are going super fast. But if you changed your mind, then things will fail, right? And we'll see more of this in the file system case. But essentially, this is some of the things you can do. You can kind of, if you can predict what you're going to use, you can keep those. The other thing that they do is PowerPoint and all those things. They assume that you're going to come back to it again. So when you exit your process, all the pages are sort of given up, but not really, right? your system keeps track of all the pages that were accessed by the PowerPoint. So if you start PowerPoint immediately again, then your system, then it will be very fast. Many of you must have noticed this, right? So if you start the PowerPoint the first time, it's very slow. Exit out of it, start again, then it takes a very fast, because even though the pages should have been thrown out, they're not thrown out because it assumes that this is a good program you're going to use again. So you can learn these things, like your IE and all those things can be learned again. So next time you start it, everything is there, you kind of go. And you have to make sure that you're not violating something. You have to make sure that data that has to be reinitialized will be reinitialized. But your program and read-only data can be reused again, so you get good performance, right? The other issue is the notion of how big the page size is, right? The page size affects all this stuff because the page size tells you what your working set is. Working set, we're defining it in terms of the number of frames. So the larger the frames, you may be able to capture a lot more of the content, right? And it affects you in terms of TLB, right? Because the more pages you have in the working set, that means you need more TLBs to map those. But TLB size is fixed, right? So one way to keep more stuff in TLB would be to reduce the number of pages you have. So in the case that we talked about where we went through 10 pages, if I increase the size of the frame by 4 times, right? So 0 to 3 would be now in the new super frame. 4 to 7 would be the next big frame and all those things, which means that you now have fewer pages, which means that you need fewer TLB entries, so you get good performance, right? So that's one reason your program, how you go to the arrays, affect what the TLB size should be, right? What the TLB size you need, and so larger frames are good because larger frames means that you now have fewer pages in your working set, which means that you get better performance, right? But larger frames also means that you're going to waste a lot of memory. So in real systems, not the desktops, but in real servers, which includes IT and M1s, they can have multiple different pages. They actually do, Deck Alpha used to do that. They have multiple different pages. It's much more complicated, but basically you can have different pages. So you can take the same page and map it in different sizes, right? So you can dynamically change the frame size to match what your working set is. So you can change to say this particular frame is now 4 megs, right? The hardware has to be much more complicated. But if you do that, so for your entire program, you start off with small pages, and then they call what they call super pages. So they can basically say, these 4 pages that you're using over and over again, I'm going to define them as super page. The hardware will know about it. So you get better TLB hits. It becomes much more interesting in terms of building the hardware, in terms of managing the software. But you can go through multiple different iterations. And so that way you get the best of both worlds. Your pages start out small. They kind of get upgraded to a larger size depending on what your working set is. And we don't tend to do that for desktops and stuff, but servers, they try to do that's a normal thing, right? To give you a sense, if you, depending on, the loop iteration we looked at, if you change how you accessed it, you change the page faults from such a large number to a small number depending on how you access it, right? But the hardware may be able to help you if you do super pages. It can put the whole array into one page, then it may avoid the page faults, right? So that pretty much wraps up the whole notion. So virtual memory is a very important topic because it lets you as a programmer write programs without having to worry about how much memory you have, right? Depending on how much memory you have, you can move the program wherever you want. You can run different programs, add different programs, and so on and so forth, right? If you didn't have all the things we talked about, you're kind of left with writing a program where you have to assume how much memory you're going to have on the system. You're going to be on only one location, sort of what you write for your cell phone or whatever. But in the modern machines, most of you don't think about how much memory you need. You just ask for memory. Magically, it's given to you. And hopefully, if you are running on a machine with a lot of memory, your system runs fast. With less memory, you still get good performance because the system is moving all these pages, moving it into hard disk and bringing it back, such that you still get somewhat decent performance, right? It's still the case that if you have a lot of memory, you're still good. But even without a lot of memory, you're not as bad, right? When most of us use virtual memory, most of us don't even think about it, right? Most of you, I don't think you have like 16 gig or something on your laptops, right? So you have enough, you use more memory than what you have. And all the things we looked at in this module is the one which makes that happen, right? Does that make sense? If you have any questions, let me know. I mean, of course, unfortunately, we have to go to the next module. But next module sort of uses some of these ideas because we are going into the hard disk space, and some of the stuff we learned here would be helpful there too, right? So we're kind of out of time, but are there any questions about what we covered so far? If not, I'll see you on Monday.